Hello, this is quiz 5 from summer 2019, and it's on 9.3, which is Fourier cosine and sine series. So we're dealing with Fourier series of functions that are either even or odd, which means that they'll end up being expressed only as a cosine series or a sine series with none of the terms from the other trig functions. Okay, question 1. Suppose that f of t equals 2 from 0 to 1, and let's find the cosine series of f. So as always, we got to graph this thing out. Our function is 2 from 0 to 1, and we're with both of these problems, we're going to have to extend our function to either make it an even or an odd function so that it will be a cosine or sine series. And just to get some definitions in here, an even function is one such that f of t is equal to f of negative t. And you can kind of think about this as if you started at t is equal to 0 and then you went forward in time by half of a period, it would look exactly the same to you if you were tracking that function as if you started at t is equal to 0 and then went back half a period. So like we're going through negative time instead. So if we apply that here for an even function, because remember, even functions are the ones that will be represented only by cosine series. So if we just walk this back, replicating what we have in the positive t range with what we have in this negative t range from 0 to negative 1, we're going to get a function that looks like this. And if this is one period of our function, then if we extend it out, here's another period, we're just going to get a line. Our line is at f of t is equal to 2. So that is our function. Now, if we're trying to find a cosine series, our series will be of the form, so f of t can be approximated by a0 over 2 plus the sum from n is equal to 1 to infinity of an cosine of n pi t over L. And then remember that an, our coefficients here, are represented by 2 over L, integral from 0 to L of f of t cosine of n pi t over L dt. Now we can replace some things in here. We know that L is the half period of our function, and since we extended our function to run from negative 1 to 1 in one period, that means that our half period is just 1. So I'll do some replacement over here. N pi t, that looks good. Okay, then what does this f of t get replaced with? Well, that's just what our function evaluates to on this interval that we're integrating over. And since our function is equal to 2 at all times, we can just replace that with, our function is not, our function is equal to 2. What am I talking about? Yes, 2. Our function is equal to 2. And I'll factor that out as a 4 right there. Okay, so let's find an, just to start off with. That's taking this integral right here. We will have 4 times 1 over n pi sine of n pi t on 0 to 1. Well, the sine of n pi in here for integer n is just going to give us 0 at all times. So that's 0. And the sine of 0 will also be 0 all the time. So, in short, an must always be 0. The thing is, what about a0? Because remember, we always have to compute a0 separately. So if we set up our formula for a0, that's just the same formula as what we used for an. So 4 integral from 0 to 1 cosine of n pi t dt, except instead of n is just some arbitrary integer, we'll specifically set n to 0. So doing that, we get a 1 in here. The integral from 1 from 0 to 1 is just 1. So a0 is equal to 4, and since our function is approximated our function is approximated by a0 over 2. That will give us 2. And since all of our an's in this sum here are equal to 0, that entire sum just disappears. And this is the cosine series. Although it may not really look like it, this is the cosine series of our function f of t is equal to 2. Let's grab this second guy over here and do question 2. So I talked about what an even function looks like. Now we're going to have to talk about odd functions for our sine series. So we have a function that's equal to some a from t between 0 and pi. So let's just call this a. We'll call that x value pi. And we're looking for a sine series. So I said that an even function is one such that f of t is equal to f of negative t. Well, it's not an even. Well, an odd function just takes it one step further. F of t is equal to negative f of negative t. So not only are we reflecting our function across the y-axis, we're also going to reflect it across the x-axis. So you kind of have this flip around the origin kind of taking place, where we have to reflect over both axes at the same time. So that gives us this kind of function here, where we have negative a, and our function is just continuing there. And if we wanted to put some more periods on here, we could just continue our function oscillating every pi unit like that. Okay, I got rid of the axes. Whoops. There we go. Okay, we have negative pi. Perfect. So we're at the point where we can just go and solve for things. A sine series in general will be of the form, so f of t will be approximated by the sum from n is equal to 1 to infinity of bn sine n pi t over L, where an is 2 over L, integral from 0 to L, f of t sine n pi t over L dt. In our case, L is the half period of our function, and since we, L will always be the half period of our function. I shouldn't have said in our case. And since we extended our function so it could be represented as a sine series by adding another pi's worth of period to it, the period of this function is 2 pi, so the half period will just be pi. So I'll replace all of those L's with pi's. That will cancel things out here pretty nicely. We'll just be left with nt inside of here. And this f of t, like usual, is just what our function evaluates to on the interval that we're integrating over. So that's just a. Okay, let's compute an. An is 2 over pi times negative a over n cosine of nt on 0 to pi. This gives us negative a over n times negative 1 to the nth power, because the cosine of pi t will just be negative 1 to the n, and this just gives us negative a over n. So rewriting some things, an is 2a over n pi times 1 minus negative 1 to the nth power. So writing our Fourier series overall using this guy right here, we can say that f of t is approximated by the sum from n is equal to 1 to infinity of 2a over n pi times 1 minus negative 1 to the nth power times the sine of nt. There we go. So this is an answer. This would be accepted, but one little tweak that we can make to this to make things look a little neater is to recognize that this term right here, this 1 minus negative 1 to the n, will evaluate to 0 for all even n, and will evaluate to 2 for all odd n. So what we can do is get rid of it, change that to a 4, and make this just say n odd. It's a little weird, but that works. And one final thing, we could also, and they like to do this a lot of the time, factor out any just coefficients, anything that's not changing. So 4a over pi could come out here, and we just have 1 over n sine of nt in there, and this is the sine series representation of that function that they gave us right here. Okay, and we are done. These were pretty easy ones to go through, although I'm not sure. You should probably do some more practice doing, more complicated Fourier cosine and sine series, ones that make you do what's it called, the integration by parts. So let's say we were trying to approximate, instead of a, we were trying to approximate t. We would need to do some integration by parts in the middle there, and that's something that I have not gotten any practice with because I have a very bad habit of putting these kind of things just into an online calculator because I can't be bothered to do the integration. Very bad habit. Don't do that. But I do like how Dr. Chen, throughout the entire semester for summer 2019, didn't make the class do any kind of crappy integration. I'm not so sure that'll be how it goes down for my midterm on Tuesday. But hopefully this was helpful for you, and have fun making some Fourier series of your own.